I would like to thank the possibility to have a short presentation here about the 3D visualization in anatomy. So first I would like to tell you about my background, so why I'm working with the 3D visualization in anatomy. I was teaching anatomy in the Veterinary University of Budapest, and then I made my PhD about some questions of the different type of turkeys. And I wanted to make first, I want to make the measurements of the air sac system of the turkey. So the body of the birds contain a lot of air because they need to be lightweight, and this air sac system is a kind of complicated system inside of the body, which can be nicely measured with the CT. Everybody told me that when I started with this project that it will be very easy because selection air from the different tissues is very easy. We just put all your images in our reconstruction program and it will be made in seconds. Then I got back some images from the very specialists of 3D reconstructions, and then I asked the guys, okay, but that part of the body, oh sorry, so that part of the body, for example, contains air, but it doesn't belong to the air sac system. So how we can do the separation? And then he said, oh, but I don't know anything about the anatomy, so you should do it by your hand. And then I said, okay, but that's not automatic segmentation. So how you can facilitate the automatic segmentation on the bodies? So then we started to create some cross-sectional anatomical atlases which could help and facilitate our work with the diagnostic imaging. All the doctors know about who are working as a radiologist that the radiology starts with the anatomy, because otherwise you won't understand the images, what you are seeing. And many of the doctors who are working with the diagnostic imaging know all the books, not these books because they are made for veterinary use, but they know the cross-sectional anatomical works. So we also started to create some cross-sectional anatomical work, but I always felt that the methods we've been using 10 years ago, using a circular saw for making cross-sectional anatomical, or a bent saw for making cross-sectional anatomical images, that is too rough for making real good 3D imaging from the real anatomical pictures. Because you could create very nice 3D creations from CT images, from MR images, but you cannot really create nice 3D images from the real colorful anatomical pictures. And the problem is if you're making anatomical reconstruction from a CT image or an MR image, it only contains grayscale information. So it doesn't tell you, for example, you could see two vessels beside of each other and you cannot really tell whether it was a vein or it was an artery, whether it was a duct or it was just a vessel. This you can only see on a colorful image. So when I tried to work with my circular saws, then I always was trying for a better method, because this is the 3D or the other plain image what you can get, for example, from a whole pig. So first it looks like a landscape picture from an unknown painter at the end of the 18th century, but in the reality it was a pig cross-sectional body created in a total different plane. So this is what you can get from a rough image. This pig was made with 6 millimeters of slice thickness. So then we were just checking the literature, how we can go much more detailed with our colorful anatomical images. And then we found the Visible Human database. The Visible Human database, it was created at the middle of the 90s in the US. So there were 2 body donations from 2 prisoners, and they donated their body after the execution. They made the CT images, the MR images, and then they put the bodies in a cylindrical mill, and then they milled the body with 1 millimeter of slice thickness. And then they created a database who anyone can have access to it, who is paying for it, of course, and then can create its own, her and his or the team own images from these colorful images. And all these images have a very much higher resolution than the diagnostic images have. Because the diagnostic imaging have a normal medical CT will have a resolution of 512 times 512 times per square. But these images, it depends on what camera you're using for taking the photos, can contain 4000 times 2000 times pixels per image. So this is a much better way to make it. So our workflow while we are creating our images is that we put our object or cadaver or whatever first in the diagnostic imaging facility. So first we CT the image and MR the image in the same position. So it's very important that through the whole process the object has to be in the same position, because then you can do the fusion and the post-processing between all imaging modality what you have been doing. So first it is put in the CT, then the MRI, and then it's deep frozen to minus 80 degrees of Celsius, and then we do the milling of the object, then we take the pictures, and at the end we do the image fusion among all these modalities, and then we do the reconstruction of on our images. It can be mainly done with manual reconstruction, because then you have to reconstruct all the things one by one, but you can also use the automatic image reconstruction from the CT and MR images, and then you can check on your manual images what you have done, or a little bit speed up your process. And then at the end you can have such images. For example, these are fusion images. Maybe you can see on this cat that the cat was milled in cross-sectional direction. You can see the each consecutive scan, but this image was created in a totally different plane. It was created in a coronal plane, but on this image you can hardly recognize that it was not created in the coronal plane, the color image. So it's not like the pig was. So then we have seen that this process is working, and then we made our first trial. It was made with a very old industrial milling machine back in Kaposvár. We made it 2 years ago, but I think you can see how great resolution we have on our image. That's, for example, the hippocampus of a dog. This has an area of maybe 5 square millimeters, and you can see on these pictures we could go also much deeper. That's a 400% magnification of the image, and still you can see all the tiny vessels and all the structures inside, which you could never have this resolution with a normal medical diagnostic method. Of course you can have micro CT, you can have small animal MRI, but for example the small animal MRI you can put only a rat in it. You cannot put a dog in it, or even an elephant if you want. That's our goal, of course. And somebody was asking me, so why we are not making any whale? We will make a whale, of course. So the next trial was, when we knew that it's working, then we were planning to make a brain atlas from a cat, but the problem was, and we were kind of lucky with it, that the cat had brain tumor. So now we have also nice information about the brain tumor. So the first we had this cadaver, then we filled the cadaver with the resin that we can easier reconstruct the arteries, because then the arteries remain red during the process and the veins were just blue or a little bit blackish. So it was very easy to automatically segmentate on the color images also the arteries from the vein, which facilitate our work much faster. So here is a tiny video about how does it look like a little cat with all these images. I hope the video will run. So you can see those cats were milled with a slice thickness of 0.4 millimeter. And from 0.4 millimeter images, you can just create a very nice video, but also you can easily recognize the structures. Here you can see, for example, the tumor inside of the brain. And those images you can put together or do the fusion, image fusion among the CT images, MR images, and the color images, and then you can study everything on your images what you would like to do. So here is a composite image made by the CT, MR, and the color images. And you can translate each plane to each plane, which can facilitate the work of a radiologist. Because I remember when I was working with a specialist in veterinary MR diagnostics, all the time in the central nervous system there's always a question, in this small resolution what you can have on a PET with a normal medical CT, that what's inside the brain, where is the problem exactly, and this can facilitate the work. Of course, we cannot meal all the cat because, or all the dogs, because it would be interesting when an owner comes and we diagnose your problem and here is your cat in a bag, because that would, but if we have some average animals, then it could help to translate the brain, for example, to the image, and we can rotate the color image to any plane, and we can just adjust from an average cat or from an average animal to the special MR or CT image what was made. That's a video about what you can create, what kind of reconstruction you can create with this image fusion. The surface was reconstructed from the MR images. The bony structures are reconstructed from the CT images, and then some parts will come from the color images. I have to speed up a little bit the video because the time what we have. And here you can see what I told you about. So you can translate any image to any image, or you can just have them in any plane. Now we are running with the MR image on the CT image, and then we are just going back with the MR image, but on the next, and then we can just facilitate or we can just add the color images also to our diagnostic imaging method. And then it's much easier to tell where the problem really is. And not just you can use it for diagnostic imaging, you can also create wonderful teaching aids for students, because, or for example, some specialists also. Because sometimes when you are doing a training in angiography, it's hard to understand where the catheter is inside the body. But you can show also these images to a professional or to a student, and it's much easier to understand the anatomy of the vascular system, where a special nerve is running through a skull, what kind of artery is running parallel with it, or how are the different structures and they position to each other. That was made from a dog. That was, that's the trial what we are doing now. That's a PhD work, a 3D brain atlas from Beagle dog. And whether you are believing or not, that's a surface model from consecutive transactions, 1,600 consecutive transactions from a dog brain. It was made with a size thickness of 100 microns, so 0.1 millimeter. And we didn't have more time for it because we would like to make it 50 microns, which is already somewhere at the border between histology and anatomy. So that's the surface model made from the consecutive images. Here is, for example, the vascular tree and the 3D model of the vascular tree. You can play anything after you have this digitized color images, because you can just change the opacity, you can change anything on your pictures, and then it's much easier. And you can, of course, load these models in the virtual reality. So one could just touch this model in the front of his, so you don't need plastination anymore, you don't need real printing, sorry Yuri, but you don't need the printing for those images, because you can just play with them in 3D. And you can see the quality, because on here, on this image, you can see, of course, that somewhere there are the lines for the transsectional scans, but that's another reconstruction in another totally different plane, where the original picture were taken. Of course, because we are in a medical university, we tried also this method on medical research. So in rheumatoid arthritis, because the question was how you can reconstruct and how you can just show the different arteries which are supplying the metacarpophalangeal joints. And that was the result what we could make with a CT, with a cone beam CT. And we were hoping that with our method we can just reconstruct much finer arteries. And there is the result, for example, that we could reconstruct the arteries with diameter of the 200 microns and sometimes 100 microns. So I think this method could be used also in medical research very easily. So now just some short videos. I will show you 2 videos. Every video is about 20 seconds. So that's the most hardest bone in the body. That's the petrosal bone. from the horse, and there you can see how nicely you can do the reconstruction with using all these images. And Yuri is not happy with this image because he knows that he has to print it in all these colors in 3D. And that's, for example, a reconstruction from just the coronary tree. And I hope you can see that some of the coronaries are containing here stents in it. So it's very easy to visualize also medical devices. And at the end, I would just like to show you the model, so what is created from the cat. And that was one of our models, which was created by a composite method for scanning a vascular tree made from a corrosion cast. And this was fusioned with the reconstruction of the bones of the head, and Yuri was printed it. And he printed it with an SLS, and then later he have it painted. And so we have this two-color image. And the advance with this, if you would touch like a normal corrosion cast, then you will find half of your cast in 20 seconds on the ground because it is so breakable. But this, as you see, I'm touching it and it's not breaking. So you can give it to the students and people can easier learn on all these objects. But of course, you don't need to print it if there are 100 students, because then you have to print it 100 times. You can just upload it in virtual reality if you want. So thank you for your attention.
Yeah, I would like to ask what kind of software do you use for segmentation?
So it's different because we were using the 3D slicer mainly, and after that, when you have your models, you have to modify them, and there we were using the mesh lab, the mesh mixer. So it depends on what is easier for the specific question to use. Sometimes we are just using the Siemens software what is delivered with the machines.
Excuse my ignorance, but how accessible this system is currently to students?
So you mean the objects or the models, or? So we are working on it, but we are only 3 people together working from our own budget, so it's not founded. So it's just we're making like a hobby at the moment, but hoping that it will grow much faster and we will have much more possibilities to work on.